Trajectory planning, if you look at the overall uh, block diagram of how a robotic system works. So let's say this is your tool. This is what the robot is. It's also called end effector. The robot uses it to do different tasks and to interact with the environment or to do pick and place or to do spraying or different kind of application you can imagine in the industry. Uh, these are the Cartesian positions and velocities, not velocity. These are Cartesian positions and orientation. Okay, they come from the arm kinematics. And on the left side of this, we have joint positions. So this block, it has been implemented in, you can think of like in the software of the robot. So every robot has a controller. Controller is kind of like a computer in which these equations are implemented. And then before even that, uh, if you were to simulate this robot, I mean, if you would, you can come up with some equations which can also tell you that if you input this much torque to each joint, the unit of torque is Newton meters. So let's say you you give 1 Newton meter to joint 1, 2 Newton meters to joint 2, 3 Newton meters to this, and so on. Then what will be the acceleration of each joint? And from that acceleration, you can double integrate it to find the joint positions. Okay, so this is just like if F is equal to ma. Force is mass times acceleration, or acceleration is force divided by mass. So think of this as a counterpart of force. Instead of force, we have torque. So torque divided by the robot inertia gives you the angular acceleration. Okay. We'll see this in one of the chapters. We haven't touched on this yet. And there is another block which sends each joint a desired amount of torque so that it can achieve a desired motion. It can reach the desired joint positions. So you normally this is the input to the system. We want each joint to go through some desired motion. Let's say we want joint 1 to be at, let's say, pi by 2 radians, joint 3 at, let's say, 0 radians, joint 4 at, let's say, pi radians. And the robot initially is at 0, 0, 0, 0, 0. That's at home position. And we want it to go to some other position. So that information you have to go to give to the robot controller. And that robot controller will compute the required amount of torques. Okay. So just like you want to open a door, let's say by 45 degrees. So that 45 degrees is your desired position. And you have installed a controller, let's say in the door, there's a motor which you have to control to make that door rotate by 45 degrees. So definitely you have to send some torques to the joints. That's only when the robot will rotate. Okay, in case of revolute joint, we're just considering revolute joints for the case of like just for this particular diagram, but there could be prismatic joint. In that case, you have to send forces to the joints. So what is a linear force for a prismatic joint? The counterpart of that is the torque for a revolute joint, okay? Because when you apply a force on a revolute joint, that force creates a torque. Anywhere you have rotation, so force gets converted into torques. You just have to multiply the force by a certain moment arm, by a distance between the point where the force is applied and between the axis of and the axis of rotation. So that distance multiplied by the force applied is called a torque. Okay, but our focus is this block. So what happens is you might not tell each joint to go to this certain position. All you know is, well, I know the end effector to go from this position to that position. In other words, I have Cartesian Cartesian motion, a Cartesian position and Cartesian orientation. In other words, I have the position and orientation of the end effector frame. That's easier for me to know where the robot is and where I should take it, instead of just computing the inverse kinematics part, just like coming up with these joints by myself. So obviously you have to convert it into inverse. You have to do the inverse kinematics to convert this into this, but you also have to find, also have to interpolate between uh, between these points. I'll explain what is interpolation. Uh, but trajectory planning mean planning the motion. Okay, trajectory is, you see a circular, it's almost a circle. It's not a perfect circle, but this is a circle which the robot is trying to trace. This is called a path. Path is, it's a geometric entity. It's a path that the robot is tracing. But if you want me to trace this path, let's say in 1 second, or in 2 seconds, or in 3 seconds. So if you want me to trace it in 1 second, in 2 seconds, then I also need to know the velocities with which I have to trace this path. Okay, let's say you want me to go from here to here in 1 second. That's a different velocity than going from here to here in 2 seconds. That's a slower velocity because I'm taking more time to reach there. So when the timing information is combined with the path, we call it a trajectory. So trajectory is a path plus timing. Okay, trajectory is when you specify not only positions but also velocities and accelerations. Okay, so that is the simplest definition of the trajectory. And by trajectory planning mean, just in case you gave me the initial point and the final point, so what should be the path between the 2 points? Shall it be a straight line, or it could be an arc, or it could be exact certain points that I have to trace while going from the start to the end? Okay, in other words, it's a point-to-point motion where the shape of the path doesn't matter. I just go from there no matter how I go. Or is it a tracking application where I have to trace a certain exact path? Let's say you're welding, so you cannot let the robot go off this position. You do not want the robot to go off this position. So there are two types of motion: point-to-point motion, and motion through a sequence of points. We'll see that later. But right now, I gave you the definition of the trajectory. Trajectory is the path that the robot traces, plus the timing information, plus the amount of accelerations and the velocities, which must be uh, uh, achieved while going from one point to another point. We always have restrictions on these velocities and these acceleration. We don't want it, like for example, if you want me to go from here to here, and you give me 1 second, and you know that this robot might weigh as heavy as, let's say, 1000 kg. Is it possible to go from here to here in 1 second? I don't think so, because of the inertia of the robot, because of the mass of the robot, because of the dynamics of the robot. So what kind of velocities and accelerations are possible to achieve and what are not? That's the problem of dynamics also. But we can also in trajectory tell you that what should be the restrictions on velocities or accelerations. Or we can also, the trajectory planning also deals with whether a certain desired motion can be achieved or not. And if it can be achieved, then how? Okay, so this block deals with it. And there is a complete chapter on this in the textbook, chapter number 7, that's called trajectory generation. Okay, so I want you to read this introduction. It's very important. I explained everything from here. So wear points, what are wear points? Wear points mean I want to go from that to here, but I want to go where some points. I want to go, I want to visit that one. For example, you want to go from here to university, from Peshawar Sadr, let's say, to university, but you want to go via Kant. or you want to go through ring road. So what are the intermediate points that you want to visit? So those are called via points. These are intermediate points between the initial and final positions. Okay, so this is the general introduction. Uh, and this is an example where you're given x initial. X initial mean you are given three positions of the end effector. It's here, and three angles, which we also call orientation. Together, these three angles are called orientation. They can be roll, pitch, and yaw, which means one is about x of the base frame. Okay, one is about y of the base frame, the green one, and one is about z, the vertical one of the base frame. Or they could be Euler angles. Okay, and we can represent this orientation by a rotation matrix as well. Okay, we just convert these three angles to a rotation matrix. But let's say this is given and the values are here 0.6. So the end effector, this point has 0.6 meter along x-axis, its displacement, minus 0.12 along the y-axis. Y-axis is there into the page, so it's little here, so it's negative. And my 0.25, so the height of this along z 0.25, that is the x z position, and then 40.3 about x. You see it's rotated about x. Look at this end effector in degrees, and 0 no rotation about y, and 90 degrees rotation about z. So we did some inverse kinematics and we found that corresponding to this initial position and orientation, these are the joint angles. Minus 171 for the joint 1 degrees, 112 for joint 2. Okay, so that is your joint 2. This has come all the way down. And minus 31.8 is for joint 3. And similarly, the last three joints are these. Where? 1, 2, 3. Okay, 41 minus 10, and these are so 6 joints. This is 6 degrees of freedom on this, a Puma 560. Okay, and now where I want it to go is to go from initial to a final position, which is this 0.38 is the x position, then y position, z position, and three angles, and then I convert that into joint space also. I do the inverse kinematics and I find what should be the joint angles if we want the end effector to be in that pose to achieve this position and this orientation. So now we know the initial Q, initial 6 values of theta, joint variables, and final Q. Now the question is, we cannot make a jump directly from this initial, let's say for joint 1 to this. There has to be intermediate points through which I have to go in order to go from here to here. Okay, and I'll try to be as smooth as possible. I try to be as smooth as possible. So in order to make it a good introduction, I'll also show you that. Okay, just give me a second. I want to show it in the simulation. All right. So let's say this is your simulator. So load the robot, Puma 560, this one. And now these are joints. So the frame is assigned to joints. Okay, we're not interested in that. This is your end effector, frame assigned to the end effector. This is your base frame, frame assigned to the base. Okay, and now what I want this, I want to give it a joint trajectory. Let's say I just pick up any joint trajectory. Let's say I want it to be a sans or talet. to trace this path. Okay, so right now it's just a path. We are not concerned with the velocity with which we should trace this path. So if I ask it to follow it, it would just go from that initial to final. So in the meantime, you can look at the joint values. So your initial thetas are here, and you can also look at the pose. So while we are here, now this is the initial position, Cartesian position, and orientation. Okay, and the final one is this one. So the final joint angles are here in radians. The initial joint angles are these in radians. Okay. And now if you look, well, I go from the initial position to the final position, you keep an eye on these and these. All of them change because I go there not in just one step. I go there in a in a in a continuous fashion. I go there smoothly. I don't make a jump. I just follow. See, I slowly change my positions and orientation, and the angles are changing in the middle. Okay. So now we need an equations where you give me just initial position and you give me final position, and you might also give me initial velocity. Initially it might be zero, and you might also give me final velocity. Should I stop there? Or I just be there at some velocity? I should reach there with some velocity. So if you give me the initial information and the final information, I can come up with some equations which can give me the intermediate points where I plug in these values, the final and the initial and the final, and then it can give me the intermediate points, these values, these thetas. Okay, sorry about that. So you can also step it. So look and keep an eye on these theta. So now we're going towards some equations which can give us these intermediate, because the operator or the guy who is using this robot in the industry, he will not give you the intermediate information unless he knows the path and he just somehow teaches this path. But if it is not given, we can also find it analytically. Analytically means we can also find it mathematically. Okay, so that will give us a good insight into this problem. So let's proceed. Okay, before I bring in some math, what is the goal of trajectory planning? Trajectory planning, it generates the reference inputs to the motion control system. I told you that this is our motion control system. This is the reference position for it. Reference means this is what it has to achieve. This is what it will send a command to the robot. Let's say this is your robot. Command to the robot so that Q matches exactly the Q desired. That's what the job of the controller is. Okay, and who gives this Q desired to this? The trajectory planning block. That's also done in software normally. Generate the reference inputs to the motion control system, which ensures that the manipulator execute the desired or planned trajectories. Planning involves generating a time sequence of the values attained by an interpolating function, typically a polynomial of the desired trajectory. What is an interpolating function? If you look at this problem, and if you had given me just the initial one, initial position and the final position, and I wanted this intermediate thetas to be found, this is called interpolation, because I only know this one, I only know the final one, I need to know the middle points, the intermediate points. This is called interpolation. Extrapolation is when you give me one point and you give me another point, and I have to point a point beyond that. Let's say let's say this is point number one, this is point number two, but somehow I need to find this point number three, which is out of that range. Interpolation is you give me the first and the last, and I need to find the something in between. Okay, so trajectory techniques, there are two techniques to generate trajectory. point-to-point motion, where the initial and final point of the path are assigned, and we don't care what is the shape of the path. All we are interested in to go from this initial position to that, whether we follow a straight line or we follow an arc, it doesn't matter. Or we follow a circle, it doesn't matter. Okay, so let's look for a straight path. Uh, well then, okay. Okay, so the final path doesn't matter. And in a motion through a sequence of points, when a finite sequence of points are assigned along the path, let's say the path is circular. So you have to give me every point along the circle so that I can trace it exactly. Okay, so these are two types of motion. Normally, think of the welding application, so you have to follow a certain sequence of points. And this is a pick and place application, let's say, where you need to pick something and you have to place something. As long as there is no obstacle around the robot, it doesn't matter whether the robot goes in the straight line, the indefector goes in a straight line, and it goes in an arc, as long as it is just picking it from a point and placing it some other point. Okay, so sometimes the path of the shape of the path matters, sometimes it doesn't matter. Trajectory planning in joint space versus trajectory planning in operational space. We converted everything into joint space right in the beginning. We did it with the initial Cartesian position and orientation, and we did it with the final Cartesian position and orientation, and we converted into joint angles. And then we do interpolation in the joint domain. I mean, we just take these thetas and these thetas, and we find intermediate Q points. We could have done that with the Cartesian positions. That would be the planning in Cartesian space. But right now, let's plan the trajectory in the joint space. Joint space means we take the initial joint positions and final joint position, and we give you the intermediate joint positions. Okay. In the Cartesian space, it would be we would take the Cartesian initial Cartesian position. We wouldn't do inverse kinematic, and we would take the final Cartesian position, and I would give you, through some mathematics, I would give you the intermediate Cartesian positions. Okay. Ultimately, the objective is the same, to make the robot go from one point in space to another point. But there are two ways to approach it. In the joint space, where you take initial joint position and final joint position, this is easy. We'll see. And in the Cartesian space, where we take this and that. So, okay. Smooth trajectories are required by the actuators to exert joint forces which do not violate the saturation limit. Okay. Whenever we do rotational motion, let's say opening the door example that I gave you, you open the door smoothly. It doesn't go in a one jump. You don't want it to open in like in a half a second or something, unless you want to break it. Okay. Similarly, we want the trajectory to be smooth. Smooth trajectories are required by the actuators because every joint has a DC motor, let's say an actuator there. That actuator, if you want it to rotate without vibration or any problem, you have to rotate it very smoothly. Okay, that means the intermediate points between the Q and final, Q initial and Q final, they should be the more the better. जितने ज़्यादा होंगे उतने करीब करीब होंगे, उतने ही आपके motion में jerks नहीं होंगी. There will be a smoother motion. Okay. All right. Which do okay. The path is the locus, the collection, the locus of points in joint space or in the operational space. When आपको कहना it's the geometry, it's a collection of points that you follow, which the manipulator has to follow in the execution of the assigned motion. It's a pure geometric description of motion. We don't care that whether we are achieving that path in 1 second or 2 seconds. We just care that okay, we have followed that path. Okay, just like you go from one city to another city, you follow a certain path on the Google map, but you don't show that what was your speed while you were following that path. So you just cared about the geometry, the shape of the path. Trajectory is the path on which timing law is specified. Trajectory is the path when you have been, you care about velocities and acceleration as well. Okay. All right, so let's see and do an example, and then I'll come back to that slide. So for that motion that you saw here, initially this was the initial, and this was the final. I also need to know the positions and orientation in between. Okay, so let's say I have somehow found them and they are here. This is how I will go smoothly change my orientation. Z is initially up. It's let's say I show you here. Okay. Let's say I show you. Yeah. See, I show you that in the middle. It's changing. This frame is changing its orientation. Okay. I've just captured those orientation here and I'm showing you at one point. But what I'm more interested in is look at each joint. While joint 1 was supposed to go from minus 170 degrees to minus 110 degrees. That was what was given. From minus 171 degrees to minus 112 degrees. How it goes? It goes in a very smooth way. It goes from minus 71 to let's say minus 169, minus 168, minus 160, minus 150, minus 140, minus 130, and then it goes there. Okay. Similarly, joint 2 was supposed to go from 112 degrees to 109 degrees. And look at the shape of the path. It's very smooth. It couldn't be smoother than this. Okay. And it also tells me that in the middle, its rotation is faster. In the start, it's very slow. In the end, it's also very slow. That's why you see the curve. Okay. Similarly, joint 3 goes from minus 30 to that. And joint 4, joint 5, joint 6. How these curves are obtained, that is our next topic. Let's say we are considering the point-to-point motion first. Point-to-point mean all we care is about the initial points for each joint and the final points. Initial points for each joints and the final points. Okay, so let's look at that. Now let's do some example, some math, which will give us that those joint positions in the middle. Okay. So let's say we want to generate a trajectory. It's a function of time. That means it's not just 2 points. It's whenever the time changes, let's say from 1 millisecond to 2, up to 2 milliseconds, Q will be something else. Up to 3 milliseconds, Q will be something else, and so on. It describes generate Q of t, describing motion of a manipulator joint from some initial Qi to final QF in a given time, and there we are also given time constraints. So that's why we call it a trajectory. Okay, we just don't call it a path. Initial and final velocities are also given. Let's say they are given and they are at time t, initial time, the q is qi. Okay, let's say this was for first joint, it was -1. In the previous example, it was what? It was minus 170 degrees. Minus 171 degrees. And let's say at some final time, TF, we're given QF. And QF was given as minus 112 degrees, minus 112.5 degrees. And let's say at TI, initial time, yeah, it could be 0. Let's say you're just starting from the beginning. The velocity was 0. We started from rest. We were not moving already. And at the final time, I want to reach there with some velocity. But in order to make it easy, let's say that is also 0. But it cannot. It might not be always 0. Let's say I want you to reach that certain point. जैसे आप एक शहर से दूसरे शहर में जाते हैं, मैं कहता हूँ आप यहाँ से यूनिवर्सिटी जाते हैं, आपने बीच में से ताकाल से गुजरना है और वहाँ पे आपकी स्पीड जो है ना, ताकाल में आपकी स्पीड 50 किलोमीटर पर आवर से कम नहीं होनी चाहिए. That means ताकाल is my final point and I have also a final velocity to be to achieve at that point. I don't have to stop there, okay, because I'm going elsewhere. Okay, so now this is the only information they are given. Call them constraints. You are given 4 constraints. ये constraints ही है ना, because इस time पे आपने इधर होना है या आप already इधर थे. इस final time पे आपने इधर होना है और कहीं नहीं होना. आपने rest QI इस initial velocity से start लेना है और initial final velocity भी given है. ठीक है. What we want to do is, if you look at this path, we want a motion as smooth as this. And this is the plot of a polynomial. It was generated by a polynomial. Polynomial is anything that you see here. Okay, it's the variable is 1. Okay, it's a polynomial in t. T is variable. The rest are coefficients of the t, and t's order is increasing. So here the t's power is 0. Here the t power is 1. Here t squared, t cubed. So what order polynomial is this? Anyone? What is the order of this polynomial?
Third order.
Third order. That's the highest order that you see in the polynomial. Okay. And if I take its derivative, because I'm interested in velocities too. So take a derivative. So the good thing about a third order derivative is that its velocity is also a function of time. Okay. And it's even its acceleration is possible. Okay? Because you took it third order for some purpose. By purpose, you took it third order because you wanted to differentiate it. So how to differentiate it with respect to t? If you differentiate this with respect to t, okay, so this will become 3a3t square. इसको करें 2a2t, इसको करें a1, और ये constant है तो इसका with respect to time derivative 0 आएगा. So it will not show up in this expression, in this second order polynomial. And if we this double dot mean differentiated with one more time with respect to t, and this will now become 6a3t. Hello? हाँ जी, sorry about that. अच्छा, Jamal Shah, any question? Acha. So now we have got these 3 polynomial. We call it a cubic trajectory because I told you this is trajectory q of t because it shows a collection of points. Whenever we change time, q will change. And this is a third order polynomial. So this is a cubic trajectory. Okay, we get one of this for each joint. Okay. But in order to be specific, we need to find these coefficients a0, a1, a2, a3. And we can find them if we utilize the initial conditions that were given. Okay, so put here in this polynomial t is equal to ti, yeah, t naught, initial time. So your q of t naught will become equal to qi. So you get qi here because q of t naught is qi, and everywhere replace the variable t by a constant t, t initial. So this will become a naught plus a1 t naught, a2 t naught square plus a3 t naught cube, and equal to this side will be what was given, q at t naught was qi, and this is qi. Similarly, use this initial condition too. At time t0, the velocity was qi dot. So now put in this expression for the velocity, put t by t naught, replace t by t naught. So you'll get a1 plus 2 a2 t naught plus 3a3 t naught square. And इसकी जगह आ जाएगा q dot at t naught, it was